So I am going to go to the textbook here. And I'm going to go to page 166. Okay. Oh, 166. All right, this section 2.1 is entitled the Rectangular Coordinate System and Graphing Utilities. Okay. All right, now hopefully some of this is review. Ladies and gentlemen, this is the XY plane here, of which you should have at least been exposed to this somewhere in your past. We have a horizontal axis normally, but not always is it referred to as the x-axis. The vertical axis is normally, but not always referred to as the y-axis. These axes can take on different names depending upon what kind of applications. These two axes basically partition my plane up into four different planes, separate planes called quadrants. Quadrant number one is right here, bounded below by the positive x-axis and to the left by the positive y-axis. The second quadrant is bounded below by the negative x-axis and the positive y-axis. The third quadrant is bounded above by the negative x-axis and to the right by the negative y-axis. And quadrant 4 is bounded above by the positive x-axis and to the left by the negative x-axis, negative y-axis, excuse me. So these are four quadrants here. The intersection point of the XY plane is called the origin. And the first thing that you normally learn how to do in this XY plane is plot what are called ordered pairs. Ordered pairs are basically represented with parentheses, where your first entry is your x coordinate, comma, and then your second entry is your y coordinate. One thing we have to be careful with ordered pairs is not to confuse them with interval notation, as interval notation makes use of parentheses also. So we got to be careful to not fall into that trap. All right, so the first thing here is, do you remember how to plot points in this XY plane? Normally, tick marks on both axes are spaced 1 unit apart, but not always. And both axes do not necessarily have to have the same scaling. For instance, the tick marks on the y-axis could be spaced 10 units apart, and on the x-axis, maybe they could be 100 units apart. Regardless of the spacing of tick marks, both axes are linear axes, in the sense that if tick marks are spaced 1 unit apart on the x-axis, they're all spaced 1 unit apart. If they're spaced like 100 units apart on the y-axis, all tick marks on the y-axis are spaced 100 units apart. All right, so the point 03, we always start at the origin. And by the way, what would be the ordered pair address of the origin? Anybody? The ordered pair address of the origin.
0, 0.
0, 0. And the plot points, we always start at 0, 0. And to plot the point like 0, 3, since the x coordinate 0, we don't move right or left on the x-axis. We just move up 3 and then plot the point right here on the y-axis. So that would be the location of the ordered pair or the point 0, 3. Plotting the point -3, 5, we start at the origin. We move -3 units along the x-axis and then up 5 units parallel to the y-axis. 1, 2, 3, 4, 5. And there is the point -3, 5 located in the second quadrant. Sometimes ordered pairs have messy coordinates. Normally they have nice integers for their coordinates, but not always. Here's a point 2.5, 3.5. To plot this point, we start at the origin, we move 2.5 to the right on the x-axis, and then we move 3.5 units up parallel to the y-axis. 1, 2, 3.5. And there's the location of that point 2.5, 3.5. All right, -2, 0 does not lie in any quadrant. It lies on the x-axis. So any questions how we're plotting ordered pairs or points in the XY plane here? Anybody? All right, so hopefully, ladies and gentlemen, it is a fair assumption and an accurate assumption, as it really should be, that we have at least learned how to plot points in the XY plane, if nothing else. Okay. All right, so that is the XY plane. Sometimes it's called the rectangular coordinate plane or the Cartesian coordinate plane. It depends what book you look at as to what they call it. All right. Now I am going to derive for us an important formula that you will need to know when working in the XY plane here. Suppose we have two unique points in the XY plane. All right, this point here, this ordered pair address, I'm going to call it X sub 1, Y sub 1. And the ordered pair address associated with this point is going to be X sub 2, Y sub 2. Now, I'm going to connect these 2 points with a line, so I have a line segment here. We're going to derive a formula that will be able to compute the distance between these 2 points. It's called the distance formula. So how are we going to derive this distance formula, which will crank out the distance between any 2 points in the plane, regardless of where they're located at? Well, to do that, I'm going to build a right triangle here. And now I have a right triangle. Okay, this represents a 90-degree right angle here. If I project this point straight vertically down to the x-axis, it will strike the tick mark, which is X sub 1. If I project this point vertically down to the x-axis, it strikes X sub 2 as the value on the x-axis, because that's the x coordinate of this point. If I project this point horizontally back to the y-axis, it strikes Y sub 1, being the y coordinate of this point. And if I project this point back to the y-axis, it strikes Y2, being the y coordinate of this point. Any questions about this derivation so far, this picture? All right. Thousands of years ago, a fellow by the name of Pythagoras is credited with this relationship. It is actually a theorem, one among many theorems in mathematics. It basically holds true for any right triangle. And it was discovered back in BC time that if you take the longest side of a right triangle, called the hypotenuse, and you square the length of the hypotenuse, Pythagoras discovered that it is always equal to the sum of the squares of the 2 shorter sides of a right triangle. This is called the Pythagorean theorem, or one direction of the Pythagorean theorem. Okay. Now, this is only true for right triangles. So therefore, to help us derive this distance formula, we can subject this little right triangle I built to the Pythagorean theorem. Now, what would be the length of this side of our right triangle here? Well, the length is the difference between the x coordinates, between this point and this point. And to ensure that this length remains positive, I'm going to enclose the difference within absolute value. So this length here of this side of my right triangle can be represented as the absolute value of X sub 2 minus X sub 1, or you could have the absolute value of X sub 1 minus X sub 2. Doesn't matter what order you subtract here, because we're taking the absolute value. In a similar way, the length of this side of my right triangle, called the leg of my right triangle, is going to be the difference between the y coordinates between these points. And so therefore, this length here is the absolute value, I'll say, of Y sub 2 minus Y sub 1. But again, the order in which you subtract really doesn't matter, since we're taking the absolute value. Now we can subject this picture to the Pythagorean theorem. Therefore, if I take the length of my longest side, which is the hypotenuse, which is always the side opposite the 90-degree angle, I square that length. According to the Pythagorean theorem, this has to be equal to the sum of the squares of the absolute values of the differences between the coordinates. And you are looking essentially at one form of the distance formula. To actually solve for d, this distance, we would take the square root, the positive square root of both sides of this equation here. Therefore, we get d is equal to the positive square root. Now, since we're squaring this difference between the coordinates, it really doesn't matter whether you have absolute values around them or parentheses. So I'm going to drop the absolute values and just go to parentheses now. Because when you square a difference, you get a positive number always. So in fact, it really doesn't even matter what order you subtract these coordinates anymore. You're always going to walk out with a positive difference anyways. Ladies and gentlemen, this is it. This is called the distance formula. Pretty important formula. It will enable you to compute the distance between any 2 points in the XY plane, just so long as those points are unique. They're not the same point. Okay, that's the distance formula. So you might want to have that handy, either memorize that or, have that in your back pocket there. Okay, let's see if we can put that. Any questions about this derivation here? All right, let's try it out. Let's compute the distance. Let's compute the distance between these 2 points here, -5, 1 and 7, -3. Now I'm going to call this point x sub 1, y sub 1, and call this one my second point, x2, y2. It doesn't matter which one you call your first and second point here. All right, anyways, the distance between these points is the positive square root of the sum of the differences of the sum of the squares of the differences between the coordinates here. So I'm going to take x sub 2, which is 7, and I'm going to subtract off x sub 1, which is -5. Y sub 2 is -3, and then I'll subtract off y sub 1, which is 1. Therefore, the distance is going to be equal to the positive square root. This is going to be 7 plus 1, which is 8, and that's going to be 8 squared. It's going to be -4, -4 squared. So we're going to have the square root of 64 plus 16, which gives me wait a minute here. This is not right. 7 subtracted -5 is 7 plus 5, which is 12. This should be 12 squared. My apologies here, 12 squared. And so this will be 144. So 144 plus 16 is going to give us 160. So that would be the distance between these 2 points, the square root of 160. And you could simplify this square root because in 160, there's a perfect square of 16, which when you take the square root, it comes out as a 4. And this would be the exact distance between those points. 4 times the square root of 10. If you want an approximation for the distance, you would actually get on your calculator, take the square root of 10, and multiply that by 4, and that gives you like about 12.6 roughly. Okay. Normally, we'd probably leave the distance in exact form, but there's times when we do go to decimal form. Any questions how we computed the distance between these 2 points here? All right, so that is the distance formula there being used. Okay. Going to derive another formula for you. All right, suppose again we have 2 unique points in the XY plane. I'll call this point x1, y1, and call this my second point, x2, y2. Suppose instead of finding the distance between these 2 points, I want to compute the midpoint between these 2 points. The midpoint, of course, is going to be the point that's halfway in between these 2 points. I'll call it M for midpoint. Find the coordinates of the midpoint. Again, I can build a right triangle for illustrative purposes. Okay. If I project this point down to the x-axis, I hit x sub 1. If I project this point vertically down the x-axis, I hit x sub 2. Projecting this point back to the y-axis, I hit y sub 1. This point back to the horizontally back to the y-axis, I strike y sub 2. Okay. All right, so what would be the x coordinate of this midpoint? Well, if I project it vertically down to the x-axis, we can see that it strikes a point dead center in between x sub 1 and x sub 2. I'll call this x sub m, the midpoint, excuse me, the x coordinate of my midpoint. What do you think x sub m is going to be? Well, x sub m, since it's halfway in between x sub 1 and x sub 2, is going to be the average of these 2 points. So we're going to add the x coordinates of the 2 points together and divide by 2. That'll be the midpoint, excuse me, the x coordinate of the midpoint. In a similar fashion, the y coordinate of the midpoint is going to be the value halfway in between y1 and y2. I'll call it y sub m. And therefore, the y coordinate of the midpoint is going to be the average of y1 and y2. So that's to say we would add y sub 1 to y sub 2 and divide by 2. And there you go. We now have a midpoint formula. So my midpoint is going to be the point whose x coordinate is the average of the x coordinates of the 2 endpoints, and whose y coordinate is going to be the average of the 2 y coordinates of the endpoints. This is called the midpoint formula. That's another formula that is wise to have available and to know. Okay, that's the midpoint. So that'll crank out the midpoint between any 2 points in the XY plane. Any questions about how we got the midpoint there? So suppose that I can use that formula to do this problem. So find the midpoint of these 2 points here, negative 1.5, negative 9, and the other point is negative 8.7 and 4. All right, I'm going to call this my point x1, y1, and I'll refer to this one as x2, y2. To find the midpoint between these points, we use our formula. So therefore, the midpoint, the x coordinate of the midpoint is going to be the average of these x coordinates here. Negative 1.5 added to negative 8.7 divided by 2. And the y coordinate is going to be the average of these y coordinates. So negative 9 plus 4 divided by 2. And when you get this worked out here, you'll have negative 10.2 divided by 2. And this is going to be negative 5 divided by 2. So your midpoint is going to be negative 5.1 comma negative 2.5. This will be the point that will be this will be the midpoint, the point that's halfway in between these 2 points in the XY plane. That's the midpoint. Any questions how I computed the midpoint of those 2 points here? All right. Another major topic of this section is graphing equations or graphing relations or functions. And so we're going to jump right in and we're going to graph this equation in the variables x and y. Okay. Now, to graph an equation in x and y, normally we like to solve the equation for y. So I'm going to subtract x squared from both sides. And this is what you have to do anyways if you're going to graph your equation on your graphing calculator. You got to solve it for y first, the dependent variable. I'm going to spin this around and say y is equal to negative x squared plus 4. All right, now to graph this relationship between x and y, I'm going to make a table, and I'm going to compute some ordered pair solutions to this equation in hopes of plotting them in the xy plane in order to graph this relationship here. Now I'm going to choose some values for x. It doesn't matter what you choose for x, whatever you choose for x, to determine y, you're going to have to run it through this definition of this relationship. So you might want to choose some values for x that are going to, enable you to easily plot the points. I mean, although you could choose like 1 million for x, good luck in plotting that point in the xy plane. It's not going to happen. So don't choose 1 million for x. Choose nice values. Try to kind of keep them close to the origin. So I'm going to try like -2, -1, 0, and 1 and 2. These are the values I'm going to choose for x. And now I'm going to have to compute what y would be. So if x is equal to -2, y is going to be found by replacing x with -2. So therefore we have the opposite of 4 plus 4, in which case we get 0. And so therefore we get 0. So when x is -2, y is 0. And therefore I have basically found an ordered pair solution for this equation to be -2, 0. If x is -1, y will be found by replacing x with -1. In which case I get -1 plus 4 or 3. Let's let x be 0, in which case y will be the opposite of 0 squared plus 4, which is to say y is 4. If x is equal to +1, y is going to be the opposite of 1 squared plus 4, which is to say -1 plus 4, which is 3. If x is equal to +2, I have the opposite of 2 squared plus 4, which is...
Wait, you put -1, 3 at that one. It was just supposed to be 1, 3.
Yeah, this should be 1, 3. 1, 3. 1, 3. There we go. If x is 2, we put 2 in for x. We have the opposite of 2 squared plus 4, which is -4 plus 4, which is 0. And so we get 2, 0. Okay, so there we go. We have generated 5 ordered pair solutions to this this equation in x and y. And to graph this equation now, let's see if we can take a piece of graphing paper and plot those points. And by doing so, hopefully we can discern what the graph looks like. So I'm going to take a piece of graphing paper, and please do use graphing paper when working in a plane. You can download free graphing paper online and print it off nowadays. And I'll see if I can post a piece of graphing paper on Canvas for your use here. I'm going to use a piece of graphing paper. Always label your axes. All right, and I need to plot some points. So I'm going to plot the point -2, 0. Start at the origin, move 2. I'm going to assume my tick marks are spaced 1 unit apart on both axes. 2 units to the left on the x-axis, -1, -2, and we stay right on the x-axis. There is the point -2, 0. Feel free to label these points if you want to. It does clutter your graph up, but you know, you can do so if you want to. -1, 3, start at the origin, move 1 to the left on the x-axis, and then up 3, 1, 2, 3. There's -1, 3. 0, 4, start at the origin. To plot 0, 4, start at the origin, move up 4 on the y-axis. 1, 2, 3, 4. There's 0, 4. Plotting the point 1, 3, start at the origin, move 1 to the right, and then up 3. 1, 2, 3, 1, 3. And then 2, 0. Start at the origin, move 2 to the right on the x-axis, and stay on the x-axis. There's 2, 0. Can we kind of see what the graph of this equation is going to look like here? It's not going to be a line. It's actually going to be a curve type graph, a smooth curve. And I'm now going to fit through these points here. And put arrows at the end here, and you have the graph of x squared plus y equals 4, or y is equal to -x squared plus 4. So that would be the graph of this equation. This equation is not a linear relationship between x and y, and that's why its graph is not a straight line graph. This is actually called a quadratic relationship. That is a quadratic function, in fact, as we'll find out. And the graphs of quadratic functions are going to be parabolas. And this parabola actually opens downwards since we have a negative being multiplied by x squared. That negative sign means the graph opened downwards. All right. Any questions how we graph this by using the point plotting method, or by, you know, making a table and generating ordered pair of solutions here? I mean, that's how you would manually plot that graph. And you know, when you do try to graph these things manually, you want to make sure that you're robust in your choices for X. You want to choose not just all positive values or not just all negative values. You want to choose some negative and positive values, because you could get in trouble here. If you just chose only positive values, then you're only going to see what, half this graph. Do you agree? You're not going to see the other half. Or if you just chose positive values, you're not going to see this half. You only see the left half. So make sure that you are lucrative in your choices for X.
Could we do 3 instead of 5 if we wanted?
What's that?
Could we do 3 instead of 5 if we wanted?
Yes. Yep. 3 points instead of 5.
Yeah.
Yeah, you can, as long as you basically already pretty much know what kind of graph this type of function is going to, you know, basically generate. And that's why it's nice to know a little bit about these functions that we're graphing, and we'll look at those in more detail, how to remember the graphs of basic functions throughout the course. But right now, if you did not know it was a parabola, you might want to plot as many points as you could possibly plot so you can clearly see what's going on. Okay.
Okay.
All right. So anyways, that's how we would manually graph this equation here. I want to point a couple things out here. This point, -2, 0, lies on what axis? -2, 0 lies on the x-axis. And so therefore it has a special name. Any point of intersection between a graph and the x-axis is called an x-intercept. So this would be an x-intercept. All right, so this point right here is called an x-intercept. This is an x-intercept. This is also an x-intercept down here, 2, 0. 2, 0 is also a point of intersection between our graph and the x-axis. This is also an x-intercept. This point of intersection between the graph and the y-axis up here is called the y-intercept. And so this would be the y-intercept here. Okay. This y-intercept also happens to be the highest point on the graph. It is called a maximum point on the graph. And since this is a graph of a parabola, we would call this y-intercept, this highest point on the graph, we would call it the vertex point. So that is the vertex point of this parabola, and it is a maximum point. Quadratic functions are ideally suited, the ones that open upwards or downwards, for maximizing or minimizing various functions. For instance, in the real world, oftentimes revenue and profit functions are modeled according to quadratic functions in hopes of maximizing those quantities. Cost functions also are modeled usually as quadratic functions in hopes of minimizing cost. All right, how can we graph this using our graphing calculator? Well, I will now demonstrate that. So to graph this using our graphing calculator, you need to make sure you solve the equation for y in terms of x. That is a requirement. And notice I've already done that. I've already solved it for y. Y is equal to -x squared plus 4, or you could type it in as 4 minus x squared. I'll type it in as -x. So you got to go to your equation editor by hitting y equals. First, you hit your y equals button in the upper left corner of your keyboard. That takes you into your equation editing mode. Then I'm going to type in -x squared plus 4. Where do I get x from? X comes into existence by hitting this button right here. Now, even if our input variable is some other variable like t or w or z or whatever, we always use x as a surrogate for that. So this is x squared, and we're going to say plus 4. Another thing I like to always check is the window setting, as to see how the axes are scaled. So I like to hit my window button at the top of my keyboard. There's a button that says window on it. Hit window. Notice my x and y axis currently are configured to run from -10 to 10 by 1. That means on the x-axis, my minimum value is -10. And my maximum value on the x-axis is +10. And the tick marks are spaced 1 unit apart. SCL is short for the word scale. The scaling used on the x-axis is spacing the tick marks 1 unit apart. You can always change these if need be necessary. My y-axis also is geared to run from a minimum value of -10 to a maximum value of 10 with a spacing between tick marks of 1 unit. You don't need to mess around with the resolution or this change in X or trace step. Don't worry about any of that. Just hit your graph button now. And you can see how the axes do run from -10 to 10 by 1, both the X and Y axis, and that would be my graph of my quadratic function there. All right, another nice thing is when you graph a relationship on your calculator, behind the scenes is also computed a table of input-output values or a table of ordered pairs. So to access the table, if you hit your second key followed by your graph button, you'll get into your table. Blue second key followed by a graph button gets us into the blue function above it called table. And that would be the table that's generated for this quadratic function. And you can see there's umpteen number of ordered pairs. You can scroll down as far as your heart can possibly desire, and you can scroll up as far as your imagination will take you. And you can look at all the different ordered pair solutions of this quadratic function here. See that there? All right, so let's get out of this. How do we get out of a mode back to the home screen? You always hit your second key followed by your mode button to quit. Second mode quits. Takes you back to your default home screen. Let's go back to our graph. I'm going to show you how to throw some diagnostic functions at this graph. If we go into our calculate mode, how do we get into calculate? We have to precede the trace button with the second key. Second, trace gets us into calculate. I'm going to try to find the maximum point on this graph, which is the vertex point, which is also the y-intercept. We use the maximum function to do that. Hit enter. Now to find the maximum point, our calculator wants us to establish a left and right bound so as to box in this value so that behind the scenes it can perform an iterative numeric routine to find that value. So I'm going to navigate my blinking cursor a little bit to the left of that point. That'll be called the left bound. Hit enter. And now your calculator wants you to establish a right bound. Navigate the blinking cursor a little bit to the right of that high point. We'll call that a right bound. Hit enter again, and your calculator finds that maximum point. Now, this x coordinate looks like it's -2.4. That's not the case because it's -2.415 times 10 to the -6th power. In fact, this is for all practical purposes 0. This is just scientific notation form. That's a very small number, so that's essentially 0. That's just round off error that's taking place inside your registers, but we call that 0. Okay, so that would be our maximum point 0.4. Any questions how we found the maximum point?
So how did you get to the maximum again?
I go into my calculate function by hitting my second key and then the trace button.
Okay, thank you.
Maximum function right down there. Okay. All right.
Point for hitting windows again?
What's that?
What was the point for hitting windows?
Oh, the reason why I want to hit my Windows key, because I just want to kind of take a look at how my axes are configured. Okay. For instance, if you had your axes, your x-axis configured to run from 100 to 200, do you think we're going to see this graph if I had my x-axis run that way?
No.
It's not going to happen. Let's hit graph and find out. Now my x-axis runs from 100 to 200, but ladies and gentlemen, we're not going to see the graph anymore because the graph is way over to the left. Do you agree? So there might be times when you might have to tinker with the scaling on your axes so that you can see the graph that you're trying to render. So -10 to 10 is usually the default setting on both axes by 1, where the spacing between tick marks is 1. And now we can see our graph again. All right, so do we understand how we found the maximum value? I'm now going to show you how to find the y-intercept. To find the y-intercept of any graph on your calculator, we have to, first of all, graph the relationship, and then we have to go into our calculate mode. Second, trace. Ladies and gentlemen, the value function always finds y-intercepts, the value function. So to find the y-intercept, we always use the value function. Hit enter. And does anybody want to weigh in as to what the x coordinate of a y-intercept must always be equal to? What must the x coordinate always be equal to for a y-intercept? Anybody?
0.
Always must be 0. Otherwise, the point's not even going to be on the y-axis. It'll be to the right or to the left of the y-axis. So to find the y-intercept, you always let x be 0. So let's just hit enter, and there's your y-intercept, 0, 4. So use the value function to find y-intercepts. All right, questions on that? Make sense? The value function and calculate to find the y-intercept. How would we find the x-intercepts? How many x-intercepts does this graph have? There's 2 of them. There's 2 points where this graph goes through the x-axis. To have our calculator find them, we go to calculate, second trace, and we go down to the 0 function. We're going to find out later in this course that x-intercepts are also called zeros of a polynomial or a graph. They're called zeros because they're values that send your polynomial function to a value of 0. That's why they're called zeros. So to find x-intercepts, we use the 0 function. Hit enter. Now to find this x-intercept over to the left, I need to establish a left and right bound to box it in. Therefore, I'm going to have to navigate my blinking cursor so that it falls a little bit below the x-axis. Why below? Why not above? Well, below because the way this graph slants as it goes through the x-axis, I have to move my cursor below the x-axis because it projects vertically up to the x-axis at a point that's to the left of the x-intercept I wish to find. That's why we must be below the x-axis here. That's called the left bound. Now your calculator wants a right bound established. Navigating the blinking cursor a little bit above the x-axis, we'll call that a right bound. It's called a right bound because this cursor projects vertically down to the x-axis at a point that's to the right of this x-intercept. Now hit enter again, and your calculator finds the x-intercept to be -2, 0. -2, 0 is your x-intercept. To find the x-intercept over here to the right, we have to go back to calculate and use the 0 function, but we have to navigate our cursor in this vicinity though. So back to calculate, second trace, 0 function. But now we got to move our cursor over here in the vicinity of this x-intercept. And by virtue of the way this graph goes through the x-axis, slanting through the x-axis through this x-intercept, our cursor has to be above the x-axis here to establish a left bound because this projects down to the x-axis at a point that's to the left of that x-intercept. The right bound now has us navigating our blinking cursor a little bit below the x-axis. That'll be a right bound because this projects vertically up to the x-axis to a point that's to the right of the x-intercept. Hit enter again, and there's your other x-intercept, 2, 0. So what I've shown you here right now, I've shown you how to graph a relation on the calculator, and I've shown you how to find any maximum values, how to find the y-intercept, and how to find the x-intercepts. Any questions with what I just demonstrated on the calculator here, graphing calculator? Okay. Well, let's get rid of this here. And let's go back here. All right, let's go back to that function. We had y is equal to -x squared plus 4. How would I find the x and y intercepts manually? What do I always set equal to 0 to find an x-intercept? Anybody? What do I always set equal to 0 to find an x-intercept?
Why?
We always set y equal to 0, or we always set the dependent variable equal to 0. So we put 0 in for y into this equation. And when we do that, we discover that we really have to solve a quadratic equation here. So that's what we're having to deal with now, is solving a quadratic equation. Now, for purposes of using the graphing technique to solve this quadratic equation, I'm going to spin these terms around and call it 4 minus x squared. Because now I realize this is the difference between perfect what? Difference between two
Where's
squares. So therefore, it will factor into the product of conjugate binomials, namely 2 minus x times 2 plus x. That has been completely factored. Now we set these factors equal to 0 and then solve the resultant first degree equations to crank out our two x-intercepts. This x-intercept, by adding x to both sides, says that one x-intercept is 2. This one is found by subtracting 2 from both sides, and another x-intercept is -2. Ladies and gentlemen, we have our two x-intercepts. 2, 0 and -2, 0, and that's exactly what we determined from our graph, and also by using that 0 function in calculate on our calculator. Those are your x-intercepts. That's how you manually find x-intercepts, by always setting y equal to 0 and then solving the equation. How do we find a y-intercept? What do I always set equal to 0 to find a y-intercept? We always set the other variable, namely x equal to 0. Take 0, substitute in for the x variable in this equation, and then our equation collapses down to this, where y walks out of this with a value of 4. Therefore, your y-intercept is 4, or as an ordered pair, would be 0, 4. Any questions on manually found the x and y-intercepts for that equation? Okay. All right, ready for classwork number 1? We'll call this classwork number 1. Today is the 9th day of February. Classwork number 1, I'm going to give you a relationship between x and y. And problem number 1 here, I want you to compute the intercepts. Compute the x and y intercepts. Problem number 2, I then want you to graph this equation so that we're all on the page, same page. I want you to use these values for x. There you go, ladies and gentlemen. We'll call that classwork number 1. Now, you don't need a piece of graphing paper for this. If you don't have one, don't worry about it. Just try to be as neat as possible with your graph. Just make a little XY plane and space your tick marks, as closely as 1 unit apart as you can on both axes. All right, go ahead and do that.
Could you show the previous problem again real quick?
All right, does anybody feel confident enough to indicate what your x-intercept or intercepts is or are? X-intercepts.
-1 and 1.
Right, -1 and 1. How about the y-intercept? Anybody?
-1.
-1. All right. Okay, well, let's take a look here. To find the x-intercept, you always set y equal to 0. Therefore, you let y in the equation become 0, and then you're having to solve a absolute value equation. To do so, we isolate the absolute value, adding 1 to both sides, and we can drop the absolute value and set what's inside the absolute value equal to the positive or -1. You have your two x-intercepts. Find the y-intercept, you let x be 0, replace x with 0, and the absolute value of 0 is 0. 0 minus 1 is -1. That's your y-intercept. Any questions how we found the intercepts?
If you wanted to use your calculator to do that, how do you type the absolute values into like the Y1 space?
For what now?
If you wanted to use your calculator to.
Okay, I'll show you that in a second. Okay, hold on that. All right. All right. Okay, so ladies and gentlemen, now I want you to crank out ordered pair solutions of that equation for plotting purposes, for the purpose of graphing that equation. And so if x is equal to -2, you replace x in the equation with -2, the absolute value of which is 2, and 2 minus 1 is 1. So we have one ordered pair solution, which is -2, 1. In a similar fashion, you plug these other values in for x and crank out what y would be, and you generate these other ordered pair solutions here. If you were to now plot those points in the XY plane and then connect the dots, if you will, with a curve or a line, you'll discover that the graph is going to be a V-shaped graph opening upwards. Did we all get that graph for this absolute value equation or function? That would be the graph. Okay. Notice we have a sharp turning point down here. So you got to be careful not to confuse the graph of a quadratic function, which is a smooth parabolic graph, compared to the graph of an absolute value function, which is a very sharp turning point here. Parabolas do not have sharp turning points. It's a very smooth, smooth turning point down here. This is a very sharp turning point. Total difference between a quadratic function and an absolute value function. So don't get these messed up, confused. All right, now you're saying how to graph this on the calculator. Well, we could also do that. So to graph this on our calculator, we go to our equation editor, y equals, clear out any garbage, and then we have to type in the new function. And so therefore, we're going to type in the absolute value of x minus 1. Where do we get the absolute value function from? Well, if you hit your math button right here, go over to number menu, math number menu. It's the ABS function right here. That's your absolute value function. So again, how did I access that? I hit my math button, went over to math number menu, select the ABS function, and there's your absolute value function. Wait a minute, I got to go back to my equation editor here. Okay, so now in your equation editor, hit math, go over to number, select the ABS function. That's the absolute value of x. Hit your right arrow key to get out from inside the absolute value. -1. Wrong. -1. Hit enter and just hit graph. Remember, my x and y axis is configured from -10 to 10 by 1. I did not change that from the last graph. And when you hit graph, you should see the graph of that V-shaped graph opening upwards. All right. Everybody get that one done? Okay, no problem. You could find the minimum value down there by using your min function and calculate, second trace, calculate. Go down and use the minimum function now, not the maximum, the minimum. A left bound, have your cursor be a little bit to the left of that, enter. Right bound, cursor a little bit to the right, enter again, and boom. That is really 0 there, and y is really -1. Okay, so you can see there's a little round off error going on in here. All right. Notice this also qualifies as being a y-intercept, and you could find the x-intercepts the same way by using your zero function and calculate the way I demonstrated there. All right, any questions how we graph this either manually or with the calculator? All right, so that is that. Okay. All right, I'm going to close that section out there. Again, if you do any graphing or point plotting, you might want to, use some graphing paper for neatness and accuracy. I will try to post a piece on Canvas for your use. You can, print it off and make copies of it if you want, or you can get your hands on your own graphing paper. It doesn't matter. All right, so section 2.3 is the last section that I bare minimum have to cover today. I don't know if I'll have time to do anything with the circle in 2.2. Okay, 2.3 is entitled Functions and Relations. People have relations. There's also relations in mathematics too. Okay, I'm going to define what a relation is. A relation's definition is pretty simple. It's nothing more than a set of ordered pairs. So that is the definition of a relation. Here's an example of a relation. Now, this is a set of ordered pairs, and we normally enclose a finite number of ordered pairs inside braces, open brace, closed brace. That's a relation. What's a function? A function is a relation. So all functions are relations, but not all relations are functions. A function is a special type of relation. It's a relation in which no two different ordered pairs have the same x coordinates. In other words, to be a function, all the ordered pairs of a relation have to have unique or different x coordinates. If you have any duplicate x coordinates between two different ordered pairs, then your relation is not a function, it's just a relation. So I have a question for you. This is a relation above here, which is a set of ordered pairs. Is it a function? Is this a function?
No,
Okay, why not?
because there's 2 3s.
Because we have two different ordered pairs here in this relation that possess the same x coordinates of 3. That's why this is not a function. It's only a relation. Okay. So that's not a function. That's just a relation. Let's take a look at this relation here. Let's go with this right here. This is a relation. It's a set of ordered pairs. Might this be a function? Is that a function? The answer is it does appear to be a function because all of the x coordinates are unique, correct? There's no duplicate x coordinates. We do have duplicate y coordinates, but we're not concerned with that here. As long as we don't have the same x coordinates between two different ordered pairs, we have a function. That's an example of a function. So a function can be represented as a set of a finite number of ordered pairs. Okay, so can a relation. All right, when we work with relations or functions, we're often concerned with two very important sets. The first one is called the domain. The domain of a relation or a function. And the domain is nothing more than the set of all x coordinates. Set of all x coordinates. That's what a domain is. And range. What's the range of a relation or a function? The range is the set of all y coordinates of a relation or a function. Suppose I defined, or symbolically I called this function function y. Whoops, what if I called this function y? What would be the domain of this function? And notice the notation, D for domain, and the little y down here means the domain of function y. Well, it would be the set consisting of all x coordinates. And what are all the x coordinates? Well, to put them in order from smallest to largest, left to right, we have -20. That would be in the domain. -1 would be in the domain. 10 is in the domain, and 16 is in the domain. That would be the domain of that function. It's just a set consisting of all x coordinates of all the points in the function, or all the ordered pairs in the function. The range of this function, denoted as r sub y, r for range, is a set of all y coordinates. Now, 4 is a duplicate y coordinate here between two different points, but just because it repeats twice, we don't have to repeat it twice in the range. We just list it once. So we got 4. We would probably have 3/4 next. Wait a minute here. You want to put these in order from smallest to largest, because your author normally does. We would have 3/4, comma, then 4, and then we would have 7. That would be the range of that function. Just a set consisting of only y coordinates, okay? So that's all there is to the domain and range of a relation or a function. Now, notice these domains and ranges are finite sets because we had a finite number of ordered pairs that define this function. Do you think your domain and range is always going to be finite? The answer is no. But for here, this case, it is. Okay. Any questions about the domain and range there? So one way to represent a function is to list all of the ordered pairs that define the function or the relation, enclosing those ordered pairs inside braces. But there's other ways to represent relations or functions. Another way to represent a relation or a function is to use what's called a Venn diagram. Venn diagrams are used in set theory all the time. Suppose this first set represents the domain and the second set represents the range. In my domain, suppose I have -4, -1, 2, and 3. In my range, suppose I have 4, 0, 1, 2. Suppose that -4 in the domain gets mapped or sent to 0 in the range by this relation. -1 gets mapped or sent to 4. 2 gets sent to 1, and 3 gets sent to 2. First of all, do I have a set of ordered pairs here? Does this represent a set of ordered pairs here?
Yes.
Well, yeah, I mean, these are like your x coordinates and these are y coordinates. Okay, so one ordered pair would be -4, comma 0. Another one would be -1, 4. Another one would be 2, 1, and 3, 2. So definitely it's a relation because it is a set of ordered pairs. Is this relation by chance a function? Is this a function? Well, it looks like all of our x coordinates are unique. They're different. So you are looking at an example of a function. Not only is this a relation, but it's also a function. What would be the domain? The domain is a set consisting of all x coordinates. That would be the domain. What would be the range? the set of all y coordinates. That'd be the range. Any questions how that Venn diagram represents a function? Okay. But there's other ways you can represent relations or functions, not just with a set of finite ordered pairs or by a Venn diagram. Sometimes, ladies and gentlemen, we can represent functions or relations by their graphs. Okay. Graphs are another way. Now, this is how we can determine by looking at a graph whether the relation qualifies as being a function or not. It's called the vertical line test. VLT, short for vertical line test. And this is the way the vertical line test works. If a vertical line placed anywhere in the XY plane touches a graph in at most 1 point, then the graph is a function. That's called the vertical line test. So it can basically be administered to the graph of any relation, and just by subjecting the graph to this vertical line test, we can determine whether the relation is indeed a function or not. Notice that a vertical line placed anywhere in the XY plane can touch the graph and at most 1 point. To say at most 1 point means that it can only touch the graph in no more than 1 point, but it could touch the graph in less than 1 point, meaning it may not touch the graph anywhere. But as long as the vertical line placed anywhere in the XY plane touches the graph and at most 1 point, we say the graph is a function. So let's take a look here. Suppose that I graph a relation in the XY plane, and suppose this is what the graph looks like. Why am I calling this a relation? Well, it's a relation because it is a set of ordered pairs. In fact, ladies and gentlemen, how many points or ordered pairs are on this graph?
Would it be infinite?
There's an infinite number of points or ordered pairs on this graph. The zeros indicate this graph goes up forever, okay? Even if it did not go up forever, even if it terminated right here and here, there would still be an infinite number of points on this graph. Some of which have nice integers for their X and Y coordinates, some of which have nightmarish decimals for their X and Y coordinates. There's an infinite swath of ordered pairs on this curve here, infinite number of them. Can't even enumerate all of them, there's so many. So there's no way we're going to be able to put all the ordered pairs of this relation inside a set of braces. There's no way, because we cannot enumerate all of them. There's too many. And so, ladies and gentlemen, how can I determine whether this relation is a function? I can subject its graph to the vertical line test. And all you do is you take a hypothetical vertical line, and it doesn't matter where you place it in the plane. No matter where I put this vertical line, do you agree that it will only touch this graph and at most what? 1 point. Isn't that true? No matter where I put a vertical line in the XY plane, it only strikes this graph and at most 1 point. True? Because of that, we say this graph passes the vertical line test. And because the graph passes the vertical line test, we're looking at what's called a what? It's not only is this a relation, it's a special type of relation. It's called a function. So that's a function. That would be a function. Notice all the points on this graph have unique or different X coordinates. So that would be a function. Any questions about that? Vertical line test, pretty easy test to administer. So suppose I have the graph of this relation here, Would this relation be a function? It's certainly a set of ordered pairs. In fact, there's an infinite number of points on this graph, but is it a function? The answer is, what do you think? Anybody?
No.
No, because I could place a vertical line somewhere in the XY plane, maybe like right here. And we can clearly see that that vertical line touches the graph in more than one point. Because of that, that's telling me that I got two different ordered pairs or points on this graph that have the same X coordinates. This is a vertical line. So the X coordinates of these points are the same. That's why this is not a function. This is just a relation. We say the graph fails the vertical line test. This is just a relation, not a function. Okay. Do we understand this vertical line test here? All right, now check this one out here. Would this relation be a function? Here's the graph of a relation. We have an infinite set of ordered pairs on here and here. Is this a function, ladies and gentlemen? Is this a function?
No.
Oh,
Okay, you're saying no. What does this closed circle mean right here? Does it mean that this point's actually on the graph?
Yes.
This point is actually a point on the graph. What does the open circle right here indicate? Does that indicate that this point is actually a point on the graph?
No.
No, this point is not on the graph. It's not a point on the graph. This point's on the graph, but not this one. So let me ask you this question here. No matter where I put a vertical line, will a vertical line placed anywhere in the plane touch this graph in more than one point?
No.
If I put a vertical line over here, notice it does not touch the graph anywhere. But we don't care about that because the vertical line test says it can only touch the graph in at most one point, meaning it leaves the door open for the possibility of a vertical line not touching the graph anywhere. You know what? It doesn't matter where I put a vertical line. It looks like it's only going to touch the graph in at most what? One point. Do you agree? Look at, even if I put a vertical line right through here, this is the area of concern. If I put a vertical line right through here, how many points is this vertical line touching on the graph?
One.
Only one, because this point is on the graph, but this point is not a point on the graph. This vertical line is only touching the graph in one point right here. Technically, we call this a function, ladies and gentlemen. The graph passes the vertical line test. Now, if this was a closed circle, would this be a function? If I close this circle, would it be a function then? If I
No.
close this circle, it would not be a function because we would have two different points on the graph with the same X coordinates then. So if that was a closed circle and this is a closed circle, then this would just be a relation, not a function. But the way it's graphed, that is a function. That is a function. How about the graph of this relation right here? Is this relation a function?
no.
Absolutely not. You could put a vertical line like right through here and it touches the graph in 1, 2, 3, 4, 5 different places. So you got 5 different ordered pairs with the same X coordinates. This is definitely not a function. Do we understand this vertical line test and what it can tell us? Okay. All right, so that's called the vertical line test. So it can give us a quick idea as to whether a graph qualifies as being a function or not. All right. Okay. Got a question for you, ladies and gentlemen. Sometimes our relations or functions are given to us in the form of an equation. What is the graph of this going to look like? Anybody? This is a linear equation, correct? In X and Y. It happens to be in what form?
Y equals mx plus b.
It's in slope intercept form. And so knowing that, we should be able to sketch the graph very quickly. What's the slope of this line? 1 or 1 over 1. What's the y-intercept?
2.
2, or as an ordered pair, it would be 0, 2. Zero, 2 is going to be right there, and the slope is 1 over 1. So if I go for my y-intercept, if I go up 1 and 1 to the right, I can plot another point. Up 1, 1 to the right, plot another point. Up 1, 1 to the right, plot a point. I could do this forever. Up 1, plot 1 to the right, plot a point. So we put a line to these points, and we have the graph of that linear equation in x and y. It's definitely a relation. Is this a function? Does its graph
Yes.
pass the vertical line test? Yes, it is. You are looking at a function. This is literally a function. Function. All right, you see the x variable here? The x variable we often call the input variable. Or we refer to it as the independent variable. The y variable we normally refer to as the output variable. Or we refer to it as the dependent variable. Ladies and gentlemen, this x plus 2 is called the definition of the function. It is called the definition because it basically defines what we do to an input to generate an output, called the definition. The way this function is defined is that anything we throw into it's going to have 2 added to it to report the output value. Okay, now this is a well-known fact. If 2 functions have the same definition, then they are the same function. Identical functions. So you know what? It really doesn't matter what we call the input and output variable. As long as the definition remains the same, we have the same function. So it's the definition that characterizes what a function is all about. It's not really what you call the input and output variable. And because of that, usually in higher level math, they tend to use for the output variable y, they tend to use what's called functional notation. So instead of saying y is equal to x plus 2, I could define this function symbolically like this. This is called functional notation. And how do we read this notation? We don't say f times x, we say f of x. F of x. That's how you read that notation. That's called functional notation. Ladies and gentlemen, this is just another name for y. It's just a different name for the output variable. Instead of using y, they use f of x. So what would this be saying or prompting us to do? How do we read this? This is saying f of what? F of 5. What's it saying to do?
Plug 5 in for x.
It's saying that we're going to put 5 into this function. So my input is 5. My output is going to be f of 5. So I put 5 into this function, which means wherever I see the input variable in the definition of this function, I have to replace it with 5. And therefore the output, f of 5, is going to be 7. What ordered pair have I just generated here? My input was 5, and what's my output? 7. So I've just generated the ordered pair 5, 7. 5, 7. You can bet that 5, 7 would have to be 1 point among an infinite number of points that lies on this graph. Wait a minute. Why is this function still the same as this function? Why are they the same? Because what has not changed? The definition is still the same. Do you agree? Because the definition is still the same, it doesn't matter what you call the output variable. We still have the same function. So the graph of this function is going to be identical to the graph of this function. The only difference is you would call the vertical axis not the y-axis, but you would refer to it as the f of x axis. That's the only difference. The graph remains the same because it's the same function. So this function is identical to this function here. Make sense? Same function. As long as the definition remains the same, the function is still the same. So imagination is the limit here. H of t is equal to t plus 2. Is this function the same as the other two I just showed you? Still the same function?
Yes.
Yes, it is, because the definition has not wavered. It has not changed at all. We're still adding 2 to the input. The input's called t instead of x. No big deal. The graph is still the same as the graph of the other ones I showed you. It's just that now we would call the horizontal axis the t-axis, and the vertical axis would be called the h of t-axis. Still the same function, still the same definition, still the same graph. Nothing changes. You can become very imaginative now. For instance, I could call my output variable Sparky. Sparky is equal to Skippy plus 2. Do you agree, ladies and gentlemen, it's still the same function? These are still the same functions because the definition hasn't changed. I'm still adding 2 to the input. The only difference is in graphing this, I would call my horizontal axis the Skippy axis. The vertical axis would now be called the Sparky axis. No difference, still the same function, still the same graph, because the definitions are the same. All right, how about this one here? How about f of w is equal to 3w squared plus 6w? Is this function the same as all these other ones up here? Are they the same? Is this function the same?
No,
Why is it not the same anymore?
because it's different.
Because the definition has radically changed. We're doing something entirely different to the input now. We're not just adding 2 to the input anymore. This is a different definition, a different function, a different graph. Okay. All right, so what would be f of -4 for this function here? What would be f of -4? What do I replace w with? What's my input into this function?
-4.
-4. So wherever we see w, we replace w with -4. And then we just have to abide by our order of operations and evaluate this. So -4 squared is 16. 6 times -4 is -24. So this is going to be 48 minus 24, which is going to net us an output value of 24. So if I put -4 into this function, f of w, I get out 24. So what is one ordered pair solution, or one ordered pair that would be a point that would lie on the graph of this if I was to take the time and graph this? One point we can be sure would lie on the graph would be what? -4 comma what?
24.
24.
24. That would have to be a point on the graph. It has to be because it satisfies the function. Okay. All right. So it doesn't matter what you call the input and output variable. What is important is the definition. Sometimes we can throw weird things into a function. I mean, you don't just have to put numbers into a function. You know, you could even, now this might seem cruel, ladies and gentlemen, but suppose I placed my dog Biff into this function. What's going to be f of Biff? Well, this function is going to do what it does to any input. It's going to take Biff and square Biff. I'm not sure what that would mean with the dog. And then it's going to multiply Biff by what? 6. And out comes an expression called 3 Biff squared plus 6 Biff. I don't even know what that looks like, but that's what happens when you throw Biff into the old function here. Sometimes we like to throw maybe algebraic expressions into a function. So what would be f of c plus 1? That's going to be 3 times quantity c plus 1 squared plus 6 times c plus 1. And, you know, you could go through and do all the algebra, expand this out and multiply by 3. And when you do that, c plus 1 times c plus 1 is c squared plus 2c plus 1, and when you multiply that by 3, you would have 3c squared plus 6c plus 3. Distribute the 6 in here, you got plus 6c plus 6. Combining like terms, you'd have 3c squared. And this would be what? Plus 12c plus 9. There you go. So if I put c plus 1 into this function f of w, out would come an expression called 3c squared plus 12c plus 9. Sometimes we put variable expressions into a function. All right. All right. Any questions about this functional notation here? Okay. All right. So it doesn't matter what you call the input and output variables in a function. What matters is the definition that characterizes what a graph of a function or a relation is going to look like. It's the definition. All right, back to the domain and range. Okay. I have the graph of a relation here. Everybody see this graph here? It's a graph of some relation. Is this relation a function? Is that relation a function?
Yes.
Yes, it would be. The graph would pass the vertical line test. So this is a function. What I'm going to do here, ladies and gentlemen, and what we can do together as the class here is we're going to try to find the domain and the range of this particular function, the domain and the range. Now, remember how I defined the domain earlier? The domain was a set of all what coordinates? The domain is a set of all x coordinates, correct? All right, so let's try to represent the domain of this function. Now, what's the smallest x coordinate of any point on this graph going to be? Well, that's going to be the x coordinate of the point that's furthest to the left on this graph. And it's this point here. And what's the ordered pair address of this point here? It looks like it's going to be what, -5, -3? And what's the x coordinate of this point? -5. So -5 is going to be the smallest value found in the domain for this function. We're going to try, but how many points sit on this graph though? How many points are there on this graph? There's an infinite number of points on this graph, infinite number. So there's no way we're going to be able to represent the domain as a set of finite numbers for the x coordinates. Can't do it. We're going to have to use interval notation to represent the domain here. So the smallest value found in our domain is -5. So I will have an open bracket, -5. Open bracket means -5 is included in the domain. So my domain runs from -5 up to what? Is -2 going to be found in the domain? -2? The answer is no, because we have an open circle here. This point, -2, 3, is not actually a point that lies on the graph. It's not on the graph. We can get infinitesimally close to -2 from the left. -2.01 is pretty close. -2.001 is even closer. -2.00001 is even closer. -2.00000000001 is even closer. How close can I get to -2? How close can I get to -2, albeit have a number that's slightly smaller than -2? Anybody? You know, the answer to that question is you can get infinitesimally close to -2. You can get infinitesimally close to -2. You could get as close as this to -2. -2 point a trillion zeros and then a 1 at the end. That would be very, very close to -2, albeit a smidget smaller than -2. You could even get closer than that if you want. -2.30 trillion zeros and then a 1. That's even closer to -2. But ladies and gentlemen, is -2 actually ever going to be in the domain of this function? The answer is absolutely not. Not exactly -2 ever will be in this domain. So we cannot include -2, hence we have a closed parenthesis. We must jump over -2. So in union with, not including -2, up to, what's the maximum value found in my domain? That's going to be the x-coordinate of the point furthest to the right on the graph. And this is the point furthest to the right on the graph. And its ordered pair address is 4, 5. So 4 is going to be the maximum value found in this domain. Hence, we must have a bracket to include it. That would be the domain of this function here. The domain pertains to values that come from the x-axis, because the domain is a set of x coordinates of all points on the graph. So think of the horizontal or the x-axis as being the domain. The range pertains to all y coordinates of all points on the graph. And what's going to be the minimum y coordinate of any point on this graph? Well, that's going to be found from the lowest point on my graph. And the lowest point on my graph is -5, -3. So -3 is going to be the minimum value found in the range. Comma, up to, but is 3 itself going to be in the range? Will 3 be in the range? Is 3 going to be in the range? So from -3 up to, but not including 3, because this point -2, 3 does not lie on the graph. It's not a point that even exists on the graph. So you cannot include 3, hence the parenthesis. You must jump over 3 in union with, not including 3, up to, what's the maximum y coordinate of any point found on this graph? That's going to be the y coordinate of the highest point on the graph, which is 5. And since that's a closed circle, that means this point actually lies on the graph, so we must include 5. You're looking at the range. So domain pertains to x coordinate values. Range pertains to y coordinate values. Any questions how I found the domain and range for that function? All right. Having the graph of a relation or a function is pretty easy then to determine visually the domain and range. But ladies and gentlemen, what if we don't have a graph? What if we have an equation for a function and we want to determine its domain? What do we do then?
Could you show the ranges again? I'm sorry.
Right here, this is the domain and range.
Okay, thank you.
All right. What if we have an equation? Specifically, what if we have like this rational function, f of x is equal to like 2x plus 1 over like x minus 3? What would be the domain of this function? Well, there's another alternative definition for the domain of a function or a relation. Previously, I said it's a set of all x coordinates of all points on the graph of the relation or the function. Well, that's great if you have a graph, but what if you don't have a graph? Well, here's an alternative definition for the domain. The domain could also be defined to be the set of all real numbers for which the relation or function, whatever the case might be, is defined. That's an alternative definition for the domain. It's a set of all real numbers for which a relation or a function is defined. Well, ladies and gentlemen, think back when we were working with rational equations, did we not have to place or think about restrictions placed on the variable? of a rational expression if the variable appears in any denominator? You remember that? When would this function ever become undefined? It would become undefined if we ever have our denominator become what number? If this denominator becomes what? 0? If this denominator becomes 0, then this rational function is undefined. Therefore, as far as the domain is concerned, we must insist that x minus 3 never ever be equal to 0, because if it is, this is undefined. Because you cannot divide by 0. Dividing by 0 is an undefined operation in mathematics. So therefore, we must insist that x never be equal to positive 3. And so now we can form our domain. So the domain of this function f is going to be all real numbers except it cannot be 3. 3 cannot be in the domain of this rational function, because if it is, then this will be undefined at 3. Isn't that true? If you evaluate this function at 3, f of 3 is 2 times 3 plus 1 over what? 3 minus 3. And you'll have 7 over 0. 7 over 0. 7 divided by 0 is what? Undefined. Isn't that true? So therefore, the domain will be all real numbers except 3. So here we go. From negative infinity up to 3, but don't include 3. In union with don't include 3 up to positive infinity. That would be the domain of that function. That is saying the set of all real numbers except 3. All real numbers except 3. That's what that's saying. That would be the domain of that function. All right, let's try another one. Suppose I have this function r of t is equal to 1 over the square root of t plus 9. What would be the domain of this function? Well, we got to make sure, since t appears in our denominator, that our denominator never becomes 0. So we must insist that this t plus 9, this quantity underneath the square root, better never ever be equal to 0. T plus 9 can never be equal to 0. Because if it is, this function's undefined, because you'll be dividing 1 by the square root of 0, which is 1 divided by 0, undefined. So therefore, t can never be equal to negative 9. T can never be equal to negative 9. So negative 9 must be excluded from the domain of this function. It cannot be in the domain. But ladies and gentlemen, there's also another concern. Not only are we concerned about the quantity underneath the square root becoming 0, but we're also concerned when the quantity underneath the square root becomes what? Anybody? Not only are we concerned when the quantity underneath the square root becomes 0, but we're also concerned if the quantity underneath the square root ever becomes what? Anybody?
Negative 9.
Negative, well, a negative number, correct? Because we're underneath the square root. And we discovered that when you take the square root of a negative number, it's no longer a real number, it's an imaginary number. So we must not only insist that t plus 9 not be equal to 0, but we must insist specifically that t plus 9 better always be strictly what? Greater than 0. Greater than 0. Which means when you solve this inequality by subtracting 9 from both sides, t must be strictly greater than negative 9. So not only can t not be equal to negative 9, but it must be strictly greater than negative 9. If you try to evaluate this function for anything less than negative 9, like if you try to put negative 10 into this function, let's see what happens. Uh-oh, I'm going to have 1 over the square root of negative 1, but the square root of negative 1 is not a real number. It's an imaginary number called I. This is not even defined as far as real numbers are concerned. Can't do that. So t must be strictly greater than negative 9 for this function to be defined. Therefore, the domain of this function r is going to be all real numbers that are strictly greater than negative 9, hence not including negative 9, comma, up to positive infinity. That would be the domain of this function r here.
How come you use the like it being greater than for this problem, but not the last one?
I used what now?
How come you use like the greater than for this problem and not the last one?
Okay, let's look at this last one here. Here, we're only concerned if the denominator becomes 0, correct? We don't care if this denominator is negative or positive. It just better never be equal to what? 0. That was our only concern. So we just had to make sure that x is not equal to 3 in that case. All right. But this one here, this function has an added problem. And the problem is that our quantity, our variable t is underneath the square root. So this thing gets into trouble two ways. It gets into trouble if t plus 9 is ever equal to 0, because we'll be dividing by 0, undefined. Or it also gets into trouble as far as real numbers are concerned if the quantity underneath the square root becomes negative, because the square root of a negative quantity is no longer a real number. Does that make sense?
Yeah.
So we had to, therefore, we had to be concerned with two restrictions. Number one, t plus 9 cannot be equal to 0. Number two, this quantity better be strictly always greater than 0, better be always positive, not negative. That's why we had to also entertain this other added restriction. Okay. So it really depends what the definition of your function looks like as to, you know, the restrictions you're going to have to impose on your domain of your function. Okay, maybe we can look at another one here. Let's see here. What if we have like z of b is equal to b divided by the absolute value of b plus 1 minus 4? What would be the domain of this function? When does this function get into trouble? Anybody? When are we going to get into trouble with this function? When is it going to become undefined? When would this function become undefined?
If it's a negative number,
Well, if what's negative?
the b.
If b is negative. So, but if I put negative 10 in for b, negative 10 plus 1 is negative 9. The absolute value of negative 9 is 9. 9 minus 4 is 5. The denominator is 5. That's okay.
Wouldn't it be if B is 3?
Okay. So in general, I guess I wanted a general answer. When would this function become undefined? When the numerator or the denominator is equal to 0? Which one?
Denominator.
It's the denominator. So here's what we're going to do. Off to the side of our paper, we're going to take this absolute value of b plus 1 minus 4, and we must insist that this denominator never be equal to what? It can never be equal to 0. Because if that denominator is 0, then we'll be dividing by 0. The whole function is undefined. Now, the person that said 3, hold that thought, because we're moving in closer. We're going to be ramping up to your response anyways. All right, now we got to solve this absolute value non-equation, if you will. We'd add 4 to both sides. Drop our absolute value symbols and then set this b plus 1 not equal to what? Positive 4, or I have to set it not equal to what? Not just positive 4, but also not equal to negative 4. Here we subtract 1 from both sides, and b can never be equal to 3. You were correct when you said that. That's one restriction that b must adhere to. B can never be 3 if this is to be defined. But there's another thing here. B can also not be equal to what? Cannot be equal to negative 5. These are two values that must be excluded from the domain of this function if it is to remain defined. Okay, let's put it to the test. If I evaluate this function at 3, let's see what happens. Well, this is 3 plus 1 is 4. What's the absolute value of 4? 4? Uh-oh, what happens in the denominator? It becomes 0. This is what? Undefined. 3 must be excluded from the domain. Let's try to put negative 5 into this and see what happens. Replacing b with negative 5 throughout. Negative 5 plus 1 is negative 4. What's the absolute value of negative 4? Positive 4. Oh, denominator becomes 0 again. Undefined. So therefore, ladies and gentlemen, you can see that we must exclude not only 3, but also negative 5. 3 and negative 5 cannot be in the domain of this function if it is to remain defined. You can put any other real number in for b, but never 3 or negative 5. Therefore, the domain of function z is going to be all real numbers except 3 and negative 5. So here we go, working from left to right on the number line, from negative infinity up to negative 5. but don't include -5, and union with, don't include -5, up to 3, but don't include 3, and union with, don't include 3, up to positive infinity. This is the interval notational way of saying all real numbers except -5 and 3. Those are the only numbers excluded from this set of real numbers.
Can you move it down?
Like that?
Yeah.
Okay, so that would be the domain of this function. That is the formal interval notational way of saying all real numbers except 3 or -5. Those numbers must be excluded from the domain. Okay, ladies and gentlemen, I have one last classwork for you. Hopefully this don't take too long. This is the last classwork. This is the graph of a relation. Is this relation a function by chance? Is this a function?
Yes.
Yes, it is. It would pass the vertical line test. No matter where you put a vertical line, the vertical line would touch the graph in at most one point. It's a function. I want you to find the domain and range for that function. This will be your last classwork, and I want you to cite the domain and range using interval notation. Go ahead and do that. So give me the domain and range of this function in interval notation. Now notice this graph goes down to the left and down below here forever, okay? So keep that in mind. So what's the domain and range? Interval notation is necessary here because we have an infinite number of points on this graph. All right, for the domain, did we get this? For the domain. Did we get that for the domain? Since this graph goes down and to the left forever, your domain is going to include from -infinity up to, why is 1 in the domain? I see an open circle here. Why is this 1 thrown in the domain also? Well, this point is not on the graph that has an x coordinate of 1, but this one is. So 1 is in the domain. So from -infinity up to and including what? 5? Did anybody get that correct for the domain?
Yes.
All right, now what's in the range? What's the smallest value found in the range as we come from the smallest value in the range and work upwards to the largest value? Well, this graph goes down forever. So the smallest value found in the range is from -infinity up to, is 2 in the range? Well, 2 is not in the range because of this, because there is no point here. So this point does not actually sit on the graph, but 2 is still found in the range because there is another point on our graph, namely over here, that does have 2 as its y coordinate. So 2 is still in the range. So the range is from negative infinity up to and including what? 4? That should be a range, okay? And there you go. All right, ladies and gentlemen, I ran out of time. Did not have a chance to look at the circle, but I think we can do that in passing later on in the course as need be necessary. I just have to show you, I'll show you the equation later on in this course. But anyways, there you have it. Sections 2.1 and 2.3. Just make sure you get the exam done by tomorrow night, midnight, if you haven't done so. And